This was a project I worked on at WindhoverLabs. It's a Kalman filter. More specifically, it's a multiplicative extended Kalman filter that is currently running in their software in the loop simulation using Gazebo. This is a little test that I ran to just check the stability of the filter under strenuous maneuvers. Already we can see that it's converged fairly quickly, but let me go back and actually talk about what's happening at the beginning with the graphs on the right. So this is just a debug tool that I wrote. So it's the units are pretty close, like in range. So it looks like it's off, but then they slowly converge. This spike right here on the yaw is actually the magnetometer getting its read for the drone's position. So then it does a hard clamp onto that magnetometer read. Same thing with the GPS. Before we get our first GPS read, we fully run the Kalman filter in NED coordinates. And then once we actually break into a global coordinate system, we re-anchor the NED frame onto the global frame. And in this case, we're using the WGS84 coordinate system. So here I'm just flying around. There is an altitude offset because of the difference between the way Gazebo registers altitude and the way that our software SITL um, GPS sensor registers altitude. A few things that I kept in mind while developing this Kalman filter is that eventually we'll be wanting to work in RF denied areas. So if we never get a GPS lock, we are always working in a local NED frame. Um, so that includes the yaw never latching or the barometer's altitude never actually latches onto a fixed position. If something bad does go wrong and our filter needs to reset, there are measures in place to um, clamp the yaw again and GPS. It's a little hard to see, or actually, I don't think it does it at all during this mid-flight, but at the very beginning, once yaw hits its clamp, we also see the local position get clamped to a more accurate result or accurate estimate. Um, this filter was designed to be very modular while also being MISRA compliant. So the way I did that is the sensors, or sorry, more specifically, the biggest challenge of designing this filter was getting the types to be compile time while also having um, like a unified interface for the sensors. I based a lot of this off of PX4's EKF. Like the main state machine had heavy inspiration from their work, but a lot of their code was deeply coupled, so you couldn't easily swap in and out sensors. All of that was baked in to their state estimator. But instead of doing that, instead of doing what they did, is I was able to weaken the encapsulation a little bit for greater modularity, which far increases the rate of development. Um, the biggest hurdle, like I said, was getting everything to be compile typed. So if we have one sensor base class, which is actually used in the Kalman filter loop. Um, then we can't the filter itself needs to be able to interpret it the same way, so they all need to have the same interface without using runtime typing. This was achieved by, instead of centralizing the filter's update in the filter like you'd normally expect, it is done in the sensors. We pass in the nominal state and the covariance matrix from the filter into the sensors instead of returning like the measurement matrix and the innovation from the sensor to the Kalman filter, like most filters do. This requires these sensors to complete the update operation themselves, which is why we weaken the encapsulation. But to aid in this, I actually wrote some templating scripts using Jinja and Python. So whenever a developer wants to create a new sensor, they can add it to a master YAML file and generate that sensor's template, which comes with the innovation update for the filter, and also the nominal state update. This filter specifically uses a multitude of sensors, including the GPS barometer, magnetometer, and the IMU, of course. Um, a fun or really creative addition that I had for this filter is that since the filter uses a sensor agnostic interface for its main loop, we're able to add in pseudo sensors into the filter that have specific uses in the main state machine. For example, while we're landed, there is a zero velocity, zero gyro, and fake position sensor, or well, pseudo sensors that I have that basically instruct the Kalman filter that it is or feeds it zero velocity and zero gyro readings, which greatly helps it learn its gyro bias and also prevents the position from drifting, since we just feed it the information that it is staying still. There's a couple others like that. I think there's the gravity sensor being one of them. So instead of having this all be baked into the state machine, we're able to decouple it and write it as sensors, which also allows us to modularly remove and add them for testing, for small unit testing. Um, hmm. This all of the code from the Kalman filter is wrapped in a state estimator class, which contains the aforementioned state machine. This was done because the Kalman filter class itself is super thinned out. It only takes a couple lines of code to actually add or remove a sensor, and the rest of it can be auto-generated through the Jinja that I mentioned earlier. Um, the state machine itself monitors and manages the landed state of the vehicle, the locking for both GPS and yaw, and also there's two different modes for how confident we are based off of our attitude. So there's a yaw online stage that happens right after our yaw convergence, which both fire very quickly and get us into this normal operational stage that you see us in. Um, so throughout this test, you've seen the vehicle do many high G rolls and loops, and the filter is still completely steady. Um, like here's one, for example. This was a great increase in performance from the last state estimator that the company had. The lead engineer was telling me that if they pitch too high, then it could become unstable. But as you can see, that issue has been fully fixed here. And I'm excited to see this be integrated into their actual flight software. So here I'm attempting to come in for a landing. This is one of the harder parts that I was struggling to finish. It handles itself pretty well until Gazebo has a bit of a physics glitch and does a super fast 180 on the vehicle, completely flipping it and breaking the filter stability. And then also, once the vehicle disarms, the filter kind of loses its state. So uh, when I come back to this, I'll need to fix both of those bugs. But they both happen, after the vehicle's touched ground, so it's less important. And here's some of those GPS clamps that I mentioned. But the pitch is it went a little crazy, or the yaw rather, which is what led to this divergence. So, like I said, it's all written with the sensors being runtime identifiable, but all of the types are compile time. So it can be statically analyzed, which is required for it to be safety critical. Oh, yeah, I should mention this filter uses a, history queue, or rather, it stores the history of the filter to make up for delayed sensors. So, when I was working with the company, I was hoping to complete the common filter faster than I expected to, which it took me about a month and some change to actually get it done. But I really wanted to work on VIO, which requires image processing. And so there's an expected delay that comes with that. And so to make up for it, I have this history queue that allows us to rewind sensor readings in the filter, and actually the filter itself. It's used all over in the code. And it would be best if this weren't templated, so that I know that's preferred in the safety critical code. But for the sake of developing quickly, I did use both templated simple structures and also eigen, which was then later replaced with the actual Windhover math library. Anyway, this allows us to rewind sensors when something delayed comes in and replay the filter itself as if that sensor had arrived on time. This prevents errors from stacking up in the filter because of delay in time. Okay, now to find the actual propagation itself, we on another side tangent, we use Van Loan discretization and a Joseph update, which is more stable for the Kalman filter. The actual update function is here. So you can see that we loop through all of the sensors and rewind if we need to. But what we care about most is here. So we are looking through all the sensors and seeing if they have a sample before the IMU, since the IMU and the sensors are both feeding in data to the filter. But anyway, this is just like a random sample, and so it returns an eye sensor along with it, which is right here, this old sensor. And so all the sensors can be the same thing, and the entire execution loop is just consolidated into this little thing. Um, yeah, I think that's about it. The auto generation is done, like I said, with Jinja templates. So this is for our nominal state. So if you want to change the actual state vector of the nominal, you can using this config YAML. So here we have states, position, velocity, attitude, the magnetic field, accelerometer bias, gyroscope bias, magnetometer bias, wind velocity, and then we go into the actual sensors. These two are just testing sensors. They're not actually real. And they're also not the fake ones that we use in the Kalman filter. But here's GPS position, GPS velocity. They are separated because their noises do not require any covariance between them. We also have our magnetometer sensor. The declination sensor is something that took a bit of learning to actually figure out. It measures the difference between the true north axis, or sorry, true north pole and the magnetic north pole. And so, based on a bunch of lookup tables, we're able to uh, pull up this bias for the magnetometer that differs from our um, WGS84 coordinates or even our local NED frame. Um, we have an airspeed sensor, a side slip sensor. This one's a pseudo sensor for wind velocity. The barometer, the gravity sensor uses the IMU once it's actually learned its bias to obtain the gravitational acceleration vector. This is a fake position sensor used for when we've lost horizontal tracking or if we are known to be standing still. Fake height sensor is pretty much the same thing, but it's for barometer, and also sitting still. Another thing for latching on, or before we latch on to magnetometer. Um, the zero velocity sensor is for when we're stationary, same thing with the gyro.